So I want to go over the daily two for today. So I'm going to share the screen and get to the daily two, which is for today is going to be this one, I believe. Yes, daily two number 48. Which of the following is not a force? And the answer is inertia. Okay, the answer is inertia. Let's see. And for the most part, you said that. A push or a pull, that's the definition of a force. So anything that's a push or a pull is a force. Weight is and friction is, inertia is not. Okay, so that was the answer to the first one. The second one, the bending of waves around corners. This is what you saw from the videos, okay? And the correct answer to that is diffraction, okay? Diffraction. That's defined as the bending of waves around corners. And so if you're in a room, okay, you can hear what's going on outside because as the sound passes into your doorway, now let me stop sharing for a minute. As the sound passes through the door, the opening of the door, it's able to bend around the corner. So even if you're standing with your back to the wall right next to the door, the sound is able to bend around the corner and get to your ears. Okay. And this is true. It's not because it's reflecting off the far wall. Because if you picture, this is the example that I use. If you're out in the middle of a field with a friend, like in the middle of this giant field, like for horses and stuff, and there's this barn for like hay right in the middle, and you're leaning against one wall, and your friend is around the corner leaning against that wall, you can talk to each other because the sound is able to bend around the corner. Okay, and waves can do this by the mechanism that I described in the video. Each point in the wavefront is its own source of waves. So as I agitate the sound, this air molecule will vibrate all of its neighbors in a sphere to agitate, and they will vibrate all of the ones in their sphere and agitate. And so it's able to bend around the corner by this mechanism. That's called diffraction, the bending of waves around corners. Okay, and I hope to show you that with a laser when we get to our light unit. Okay, all right, and so that's daily two number 48. I'd like to go back and talk about daily two number 47, the one from yesterday. Okay, fill in the blank. Once a wave is generated, okay, what property of the wave never changes regardless of where it travels, and that is frequency. Okay, once it is generated, the frequency of a wave never changes, okay, regardless of where it goes. All right, and looking at the responses for this, I see that the vast majority of you guys chose that, and that's terrific. Okay, that's an important point that I'm going to come back to again and again throughout this unit, actually throughout this semester. All right, and the second one was sound waves travel the fastest through solids, okay, through solids, because the particles are closer together. And the particles do not have to go as far to collide with their neighbors and transmit the sound wave from place to place. So the correct answer for that is solids. Okay, and those are the daily twos. Any questions about those? Questions about those? All right, next order of business, I want to go over Waves Worksheet 2, that's which was due last Friday. I want to go over the answers to that. So I'm going to share the screen again. And this is what you should have chosen for that, okay? So the first one, they're oriented with respect to, I believe I had drawings instead of just asking the question, but it's perpendicular to the wavefronts, both for a circular wave and for a plane wave. So for a circular wave, it goes out from the center along a radius, okay? So check your drawing to see if it does. And for a straight wave, it is perpendicular. For example, going down here, this is the rate of propagation for a plane wave, okay? Perpendicular to the wavefronts being the crests of the wave, okay? Rate of propagation goes like this. All right, for number 2, a plane wave bouncing off a curved barrier. The particles of the wavefront or the energy of the wavefront is all reflected to a single point, and we call that point the focus. And so it's like we focus those waves to a point. If we allow them to pass through, they would form circular wavefronts like this. Okay? Now, usually we don't even let them go. We collect them right at the focus. And as an example, in my video, I described a satellite dish. So if you have a satellite dish in your home, it's pointed at a satellite, and the radio waves come from that satellite, and they reflect from your curved barrier, and they're all concentrated to a point. They're all focused to a point, and that's where the pickup is. And so you pick up the signal, and it eventually becomes a TV signal or whatever. Okay. So and so yeah. Now if instead I put a source of waves at the focus, okay, and for example a light bulb, and I reflect them off a curved mirror, the light waves, which will go out as circular wavefronts, will strike the barrier and actually reflect as a straight wave. They will reflect as a plane wave. And so what that means is all the rays of propagation after reflecting, they will all point in the same direction. All the rays of propagation will point in the same direction. Okay? And that's a flashlight. So I make all the rays of light. If I bounce those rays off of off a curved barrier, they will all come out parallel to each other. And that will be a flashlight or a stoplight or the headlight of your cars or whatever. Okay? So that's an application of this. Very widespread. All right. The straight wave bouncing from a straight barrier, not quite as interesting. It would come off as a plane wave just going in the opposite direction. And that would be an example of reflecting from a plane mirror, like a laser being reflected from a mirror. It comes off just going like this. Okay. Not a whole lot of applications that come to mind on that, other than just kind of seeing around corners. Okay, you put a curved barrier like this, you can see around the corner. Light coming from over here can be seen from over here. Let's see here. Next. Okay, a plane wave traveling in a different medium, the speed slows down. The frequency remains the same, and the wavelength decreases by V equals F lambda. If the speed goes down, the wavelength goes down. The frequency remains the same. Okay, and for number 5, I saw many correct answers here. The biggest trouble that I've seen was on like numbers 2 and 3. Okay, numbers 4 and 5 looked overall, they looked pretty good. So what is the wavelength of the wave? V equals F lambda, so lambda is equal to V over F, and it turns out to be 2.7 meters for the wave in the 8 meter per second medium. If the speed goes down, the wavelength goes down correspondingly to 2 meters. Notice the frequency remains the same. Okay. All right. Okay, questions, comments on Waves Worksheet 1. Waves Worksheet 1. Okay. All right, put that away. Now the next thing I want to go through is the answers to Sound Worksheet 1, that which was due yesterday. All right, and it's titled, let me just share the screen. It's titled, If a Tree Falls in the Forest, okay? Which actually kind of begs the question, if a tree falls in the forest and there's nobody around to hear it, and when I say nobody, I mean nothing. No people, no animals, no bugs, nothing, okay? Doesn't make a sound. And I want to make a poll on this. If a tree falls in the forest and no living thing is around to hear it, does it make a sound? Make a choice. What do you think? Now, most of you said yes, but there were some that didn't. More than one person said no. All right. I'm not going to share the results. The most, okay, I'll share the results. There are the results. Okay. All right. Of the respondents, more than one, more than two chose no for this. And this is always kind of interesting to me. I'm going to stop sharing because I would ask this question, and there was one time that there were two kids in class that kind of got into it. Say, yes, it does. No, it doesn't. Yes, it does. No, it doesn't. They actually got kind of a little heated. And there is no right answer to this. You know, it just depends on on your definition of sound. So there's no. I'll never ask you that question because there's no. It depends. If you consider sound to be just this energy wave that passes through objects like the air, through a medium such as the air, just an energy wave, you know, then you probably said yes. But if you consider sound as something that needs to be perceived by something, some creature, okay, such as us, if it needs to be perceived in your mind in order to be sound, then you would say no to that question. And it just depends on your definition of sound. So it's kind of an interesting. It's kind of interesting to see what you think about that. What usually most when I ask this question, most people say yes, but there are always some that say no. Okay? And it just depends. There's no right or wrong answer. So, but it just depends on your definition of sound. So, just kind of a fun little discussion I like to have sometimes. Okay, all right. So, what are the answers to these? Mechanical waves are waves that need. What are two examples of mechanical waves? People have said sound, tsunami, water waves, waves in a spring, something that needs to be some medium of travel. Okay. I actually I haven't typed the answers in here. Maybe I should have. Sound cannot travel through the vacuum of space. Why not? Because there are no particles to vibrate. Remember, sound is transmitted by collisions between particles. No particles, no collisions, no transmission. Okay. See, can I write on this, or is this a PDF? I think this is a. Oh, I'm sharing. That's why I can't write on it. Okay. What's the speed of sound through air at 1 atmosphere and 0 degrees Celsius? 331.5 meters per second. Through water, about 1,500 meters per second from our notes. And through steel, about 5,000 meters per second. Okay? By the way, I'll never ask you the speed of sound through water. I'll never ask you the speed of sound through steel. All right? You will need to know the speed of sound through air because we'll need that to do problems. 4, why do waves travel faster in solids than they do in air? Because the particles are closer together. All right, people cited density arguments, and that's fine. The particles are closer together. So if I ask you this on the test, that's all you have to say, because the particles are closer together. Okay? Okay, number 5. Find the wavelength of the sound wave created by a 440 hertz fork in air that is at 25 degrees Celsius. And first we have to find the speed. So I'm going to get out of there and bring into my, start from the beginning. Play from start. And so that's number 5. Okay, so we have to first find the speed at that temperature. So we're going to use this relationship 331.5 meters per second plus 0.6 t, where t is 25. And I got 346.5 meters per second when I did that. Then we're going to use v equals f lambda, divide out the frequency to get lambda is equal to v over f, and the answer becomes 0.78 meters. Okay, 0.78 meters. All right. Okay, stop sharing for a minute. Please put your hands 0.78 meters apart. Please put your hands 0.78 meters apart. Yeah, that's about right. I like that. You know, far enough away. Here's a meter stick. You know, about that far apart. So this, here's a 440 hertz fork. Okay. Can you hear that, by the way? Can I get a thumbs up? Can you hear that? You hear that? Yeah, this is 440 hertz. So the compression and rarefaction, one compression and one rarefaction fits in there. You can fit a sound wave between your hands very comfortably. Okay, one compression and one rarefaction from that. Okay, get you a feel for sound waves. All right, sharing again. Getting back into this. Escaping out of this though, because I think the next one, yeah, I got to go number 6 on my. Oh, where'd it go? No, that's not it. Sound worksheet 1. Okay, sorry. A wave is generated and passes from one medium into another medium. For example, water wave passes from deep water to shallow water, or a sound wave passes from warm air inside into cold air outside, or vice versa. Which of the waves frequency never changes. Waves frequency never changes. Keep coming back to that. All right, number 7, certain sound wave has a 3 meter wavelength on a 10 degrees Celsius day. Find the wavelength when the sound enters air of 25 degrees Celsius. All right, so I'm going to play from current slide, number 7. All right, so first of all, what we have to do is we have to find the speed, okay? And the speed in 10 degrees Celsius air is 337.5 meters per second. Okay. And then from V equals F lambda, the reason we're doing this is we need to find the frequency, 112.5 hertz. Now, no matter where this sound goes, from 10 degrees Celsius to 25 degrees Celsius or anything else, the frequency always is going to be 112.5 hertz. Now, we want to find the wavelength when it's 25 degrees Celsius, right? We already found the speed in an earlier problem. We don't have to do it again. All right, and so now we can find the wavelength by putting that speed over that frequency, and it turns out to be about 3.08 meters rounded. Okay, 3.08 meters. Okay, and I saw a bunch of these correct answers. I also saw some incorrect. So, yeah. Questions? All right, next one. You're storm watching on a 25 degrees Celsius day. If lightning strikes and it takes 4 seconds for the sound to reach you, how far away was the bolt? Okay, I'm gonna stop sharing for a minute. When I used to watch thunderstorms, when you watch thunderstorms, you see the flash of the lightning, and you go 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, boom! Then you hear the thunder from that lightning, and a lot of us are taught when they're growing up that if it takes 4 seconds to get to you, then the lightning bolt is 4 miles away. Have you ever heard that? Okay. Have you ever heard that? Okay. 4 seconds, 4 miles away, right? Well, let's find out if that's actually true. Okay. Okay. Flash. 1 banana, 2 banana, 3 banana, 4 banana. Boom! 4 miles, right? All right. Well, let's do a little math and see if that's actually true. Okay. So sound is going to travel at a constant speed through the air. The speed of sound on a 25 degrees Celsius day. Oh, by the way, 25 degrees Celsius is a very comfortable summer day. It would translate to a mid-80s. Okay. All right. Well, for around here, it'd be early spring or fall, I guess. In summertime, it's hotter, I guess, from where I come from. It'd be a very comfortable summer day, mid-80s. So not out of the realm of possibility at all. So it travels this fast for 4 seconds, and it goes about 1,400 meters. Okay. How far is this in miles? Well, you people who run track know that a mile is about 1,600 meters. Okay. 1610 to be exact. So if I take this and convert it to miles, what I get is 0.86 miles. All right. So it wasn't 4 miles away. It was less than 1. Okay, so it brings the lightning a whole lot closer to you. All right, so this whole urban myth about 1 second per mile, that's completely false. I mean, that's assuming that the sound travels a mile per second through the air, but it doesn't. It travels a mile per second through water, but not through air. It travels much slower. So it's less than a mile. So when you're storm watching, it's roughly a little bit less than 4 seconds per mile. Okay. All right. We're about, check that, 4 seconds. If it travels a mile, it takes a little bit more than 4 seconds. Okay. So consider that next time you're storm watching, which is really fun. Okay, next I'm going to, I have to finish the sound worksheet 1. I'm going to have the screen a lot today, by the way, just so you know. I got a lot to show you guys today. Where did it go? Oh, here it is. All right, describe the following terms. This is just, vocabulary. Pitch is related to frequency, audible range, we know, ultrasonic, infrasonic. And then the 3 smallest bones are located in our ears. Colloquially, they're called a hammer, anvil, and stirrup, or malleus, incus, and stapes. Depend. I'm honestly never going to ask you that on a test, but maybe you'll remember it anyway. Okay, the 3 smallest bones are in your ear. Okay, and so that's sound worksheet 1. Okay, questions, comments? Okay. All right. Now the topic of the day then, and now's the time to get something to write with, something to write on. The topic of the day is something called the Doppler effect. Okay. And we're going to spend the day, much of the day, talking about this. Not all of it though. I got some. Let's see, what do I have until 2 o'clock? I have a lot of things to show you today, and I don't know. Honestly, I don't know how far I'm going to get, but I'll just get to however far I get. Okay, now, oops, why is that not working? Okay, when a sound source is stationary, it emits sound waves in a pattern that kind of looks like this. It starts at the center, and it moves out in a circular, or truth be told, spherical manner, okay? And if I consider these lines to be compressions of the wave, okay, the distance between them, the distance between the dark lines are a wavelength. Consider these to be compressions. And no matter, as these emanate outward, no matter where we are located, whether we're over here to the right, or over here to the left, or over here, or over here, the number of these as they pass our ear, the number of them are equal, no matter where I am around the sound source. Okay, so the waves emanate out from a central disturbance in an equal type of fashion. Okay, but when the source is moving, the pattern is different. Okay, the pattern is different. Now, keep in mind, if I'm going too fast on this, number 1, I'm recording this, and number 2, this presentation is located on Schoology, so you can get all these notes later if you want. All right, now, as the source moves, let's say this is the source that's moving to the right, and after one period, this was the sound wave that was emanated a little while ago, okay, when the source was here. In the time period of one period of the wave, the source moves from here to a little bit to the right. And so here, say, all right? One period later, it's right here and emanates and emits another sound wave. One period later, it is here. Now notice, each wave is circular around the source. But if the source moves, the wavefronts are no longer concentric circles. Instead, they are bunched up in the front. Can't remember if I have one more of this or not. No, we don't. So the waves in front of the source are bunched up. So if you're over here on this side, more waves pass your ear per second. And if more wavelengths pass your ear in the same medium speed, that means the apparent frequency would be higher. Okay? Then the frequency, if you're behind it, well, I'll get to that in a minute, actually. Okay? So if you're you're in front of the source as it's approaching you, then the waves are bunched up. Okay. After it passes you by, now the waves are spread out, and if the waves are spread out, fewer pass your ear per second, and so the apparent frequency would be lower than if the source were stationary. Okay. All right. This is called the Doppler effect. All right. Now, I want to get out of this. I have a simulation, but before I show that, I want to show you some YouTube stuff. So get out of there, minimize that, and get this out of the way. And this is what we would hear. I got to get my window out of the way so I can see. Okay. That's what you hear, like from that you can observe dozens of times per day if you pay attention, from all sorts of moving sources of sound. For example, a car, in this case, a train. Okay, this is the Doppler effect. Okay, or we can observe it. I have lots of these. Okay, or we can observe it here. Here is a guy on a bike. I'll do that later. Guy on a bike. Okay. Let's see. Is it this one? Okay, that's just a constant frequency buzzer. You heard the frequency go down, okay, as the source was moving towards you. And this is what happens. The waves in front get bunched up. And so you hear an higher apparent frequency. After it passes, you hear it lower, okay? Oh, by the way, as long as I got you here, this would also be observed if the source were stationary and the observer were moving. Okay, so here, the guy is just going to be holding this buzzer on the side of the path. And the guy with the bike is going to be riding past this stationary one. Okay? He's right there, standing next to the path. Now here comes a bike. Again, you hear the lowering of it's the change in frequency. This is called the Doppler effect. Okay? And oops, not that what I want. And so if I had a plane, and a plane was hovering. What do you mean planes can do that? Planes can hover? Yeah, actually there's a British one that can, called a Harrier jet. But if this plane were moving, all right, if this plane were moving, now the waves get bunched up in front. Okay. So this is what as a plane, as a plane passes you. Okay. All right, let's have some fun with this. Actually, I'm going to go to the right. 0.39 is 0.39 times the speed of sound. Let's have some fun. Let's go close to the speed of sound. Now look how bunched up they are. Okay. So look how bunched up they are. This is a plane approaching almost Mach 1. All right. They're all bunched up there. All right. Well, let's go Mach 1. Yeah, let's go Mach 1. And so that's what it would look like. So you get the shock wave right in front of the plane. So if I'm here, I'm hearing kaboom. There's our sonic boom, right? All right, well, okay, let's have fun with this. Let's go Mach 2. Let's go Mach 2. So the sound waves doing Mach 2. Let's see. Okay, how fast can this go? What's the max? Looks like, can I go down there? Go down to the corner and go Mach. Will it let me? It won't let. Oh, that's boring. Okay, let's see. Let's go Mach 3.64. Okay, so yeah. All right, so there it went. So just kind of having fun with the simulation. Maybe you know what I should do? I have a whole page of these. I should post that page in the Schoology so you can mess around with this yourself. You can play around with this yourself. But that's the Doppler effect, okay? One more time, just for fun.
The approaching train is going to take stop at this station.
And you can observe this dozens of times per day, you know, lots and lots of times if you pay attention, okay? Because it is a very, you know, it's all over the place. All right, so now getting back to this. All right, so the Doppler effect is the apparent change in frequency due to the relative motion. The apparent change in frequency due to the relative motion between the source and observer of sound. It doesn't always have to be sound, but I'm going to relate it to sound like this, okay? And then there's a couple of equations down there that I'd like you to copy down, okay? All right. Now, actually, you know what? Just get the definition down. No, actually, take down that whole screen. Okay. F prime is equal to F sub S times V over V minus V sub S. It's a complicated looking formula, but it's not as scary as you might think, okay? So for going away or from when the source is receding from you, it's F prime is equal to F sub S times V over V plus V sub S. There's only one difference in those two formulas, and that's the sign, those two equations, and that's the sign of the sign in the denominator. Okay, so I'm gonna have you get that down. Okay, and then I want to do an example of this. It's a little bit scary, but it's not that bad once you work with it. So trust me on that one. Okay. All right. Now I'm going to stop sharing. Actually, before I do that, I have these equations on the board. Okay. So now I want to go to an example. All right. A train approaches a crossing on a 20 degrees Celsius day at a speed of 25 meters per second. All right. Sorry, you're going to have to write that down. I don't have an example sheet. Okay. So a train approaches a crossing on a 20 degrees Celsius day at a speed of 25 meters per second. If its siren has a frequency of 350 hertz, what is the frequency heard by an observer standing at the crossing? Okay. So what I have is that the temperature is 20 degrees Celsius. I'm making myself a little data table here, which I will show you in just a moment. Okay. The speed of the source, that is the train, is 25 meters per second. The frequency of the source, that is the train, is 350 hertz. Okay. What we want to know is what is F prime? What is the speed? Check that. What is the frequency that's heard by the observer? Okay. So stop sharing. So this is what I got. Okay. I have the temperature being 20 degrees Celsius. We have the speed of the train, the speed of the source being 25. I have the frequency of the source being 350. what we want is the apparent frequency. Now, what I don't know yet is V. V is the speed of sound. Speed of sound, okay? That depends on the temperature. The temperature is 20 degrees Celsius. So this is going to be 331.5 meters per second plus 0.6 times 20. 0.6 times 20. I'll zoom in a little bit. Oh dear. Yeah. Okay. 0.6 times 20 is 12. And if I add that to here, I get 343.5 meters per second. Okay? That's the speed of sound. All right. Now, okay with that? My body's going to get in the way, so apologies in advance. All right? The frequency on approach is going to be this one above, F sub s times V over V minus V sub s. Plugging my numbers in, I get 350 hertz times V. V is the speed of sound, 343.5. Meters per second. Over V, 343.5 minus the speed of the source, 25. That's how fast the train is moving. Okay? Oops. Okay, so now we have some math to do. So I have 350 hertz times 343.5 over 343.5 minus 25. If I do my math in my head right, 343.5 minus 25 is 318.5. I'm doing the math in my head right. Okay, chat window time. What is 343.5 divided by 318.5? What is that? I need your help, calculators. $1.08. Is that confirmed? Thank you, Christopher. Is that confirmed? 1.08. Need a confirmation on that. Yes? Okay. 1.08. Meters per second cancel themselves out. I call this the change factor. Okay. All right. Multiply by 350. What do you get? To the nearest hertz. What's 350 times 1.08? To the nearest hertz. Come on, calculators. Need your help. 378, 378. Thank you. So 378 hertz. That's what if you you approach this crossing, just as the lights come, the gates come down, you got to wait for this train. By law, trains have to sound their sirens as they cross roads. So you would hear, as it's coming towards you, 378 hertz as the frequency. Okay, part B. What do you hear? What frequency do you hear after the train passes and is receding away from you? Okay, now we're going to use this expression. Okay, so part B. While it's going away, you hear F prime is equal to F sub s times V over V plus V sub s. The only difference is we're going to add in the denominator instead of subtract before. Otherwise, it's the same. 350 hertz times 343.5. I'm just going to ignore the meters per second because I know they're going to cancel out. 343.5 plus 25. Okay. 350 hertz. 343.5 over 368.5. Calculators. What's 343.5 divided by 368.5? What is the change factor now? 0 point something. 0 point what? 0.93? 0.93? Okay. Take that number in your calculator, multiply by 350. What is the apparent frequency now? Calculators? To the nearest hertz? I'm guessing 320 something. 328? I don't remember what the answer is. First time I'm doing this year. 328, is that confirmed? Oh, I got 326. Well, okay, depending on where you round, okay, if you rounded this or not, you're gonna get in that range. I'm not gonna worry about that. 326 hertz. So upon recession, you would hear 328 hertz. So while it's coming towards you, and goes down like that. That's a Doppler effect. Okay. If the train was going faster, okay, this change factor would be larger, either larger, bigger than 1, or larger, less than 1. And so the difference between the siren, 350 hertz, and the difference between the real frequency and the apparent frequency would be larger. So it is speed dependent, all right? By the way, this is how police officers check to see if you're speeding. They have those speed, this is how speed guns work, whether it's for the police or baseball scouts that are measuring the speed of pitches. They use the Doppler effect. They send out a signal of known frequency. They get that frequency back and they read it. And by the difference in from what they sent to what they receive, you can use a formula pretty much like this to calculate the speed. Solve this for the speed of the source, and you can get the speed with which that object is moving. So they bounce a radar signal off your car or off a baseball. And if they send it at like 1,000 hertz and they get it back at 1,050 hertz, they can take that difference, put it in this formula, and figure out how fast your car was going or how fast the baseball is going. Okay? So cops or police officers use the Doppler effect in their speed guns. Speed guns, whether it's for police or sports or whatever, they operate by the Doppler effect. The difference in frequency, it can happen with sound or any kind of wave. Doesn't have to be just sound. It happens in waves in general. Okay, we can observe it with sound with our ears. Okay, yeah, actually more on that in a minute. With our eyes. Okay, but I have to remember to mention that. But this is a Doppler effect. Okay, all right. Now, getting back to any questions. Any questions? It's kind of a scary formula at first until you use it once or twice, and then it's not so bad, okay? So I'm gonna have you do a problem or two. Well, a problem very much like this, eventually, okay? I'm not gonna have any homework today, but all right, getting back into this presentation. And I go through this example, la la la, la la la, la la, 377 according to me. Maybe it's some rounding difference. And then upon recession, it was 326. Okay. What frequency would be heard by the conductor of the train? What frequency would be heard by the conductor? What do you think? What do you think? Any guesses? No guesses? Is the conductor moving relative to the train? And the answer is no. So yes, the sound would be stationary. So what frequency would the conductor hear? What frequency would the conductor hear? Yeah, exactly. 350. Yeah, because there's no relative motion. So according to the conductor, it would be um, 350 hertz. Okay, that's the Doppler effect. It was studied by an Austrian guy by the name of Christian Doppler in the mid 1800s. Okay, and well, he hired somebody to sit on a train and play, I believe it was the note A on a trumpet as he approached Christian and then receded from him. And from this, Mr. Doppler was able to describe the effect and figure out an equation for it. Okay. Now this has had the Doppler effect is a lot more. They do a lot more with it than just see if you're speeding or not. Okay, this is lots of applications in lots of different areas. For example, and you may have heard of this, if when you hear the word Doppler, it's probably not so much in physics class, but you might hear it on the weather report. Doppler radar. Okay, Doppler radar. And this is a Doppler radar station. Inside this dome is a radar dish that's spinning around and around and around. Okay, it's a curved reflector, and it's spinning around and around. And what it's doing is it's sending out radar signals. Okay, and it's trying to see what's happening inside of a cloud. All right, let me stop sharing. Have you ever heard of no, I'm just asking. Do you ever get a tornado around here? Do you know what a tornado is? You ever see one on TV and stuff? Okay. Where I used to live was the American Midwest, and between the Rocky Mountains, actually from about Kansas to about Indiana, maybe into Ohio a little bit, 75% of the tornadoes in the world occur in that region of Earth, the Midwestern United States, okay? And the reason for that is, well, you got the Rocky Mountains in one place, you got the Gulf of Mexico in another place, and it churns up the air, making really intense storms that can spawn tornadoes. Okay, 75%. When I talked back there, we'd have a tornado drill and they would come into my room because it was in the interior, didn't have any windows. So I get a whole bunch of classes in there, and I give a little spiel about tornadoes. Give my tornado spiel, right? So I can give that to you. 75% of the world's tornadoes occur there. Now, when I was a kid, you know, in the 20th century, you would never know a tornado was on the ground until you never know a tornado was around until it was on the ground. Okay, ripping up houses and killing people and stuff like that, because they could not see the formation of them inside of a dark storm cloud. Okay, but then in the 80s, 70s and 80s, Doppler radar was developed. Let me describe how that works. A lot of tornadoes, sometimes tornadoes happen at night, so you would have no way of knowing it was there until you heard them, and by then it's not good. They say it. I've never seen one in person. I've never heard one in person. Okay, but they said it sounds like a train. Okay, barreling towards your house. And so what you want to do in a dark storm cloud is you want to get a picture of what's happening inside that storm cloud to see if there's anything going on, right? And so they send radar signals into it. And let's say they send a radar signal into it, and it's 1,000 hertz. This is the same thing as cops with their speed gun. Okay, they send a radar signal. Let's say it's 1,000 hertz. Actually, a lot higher, but let's say it's 1,000 hertz. They send it into the storm cloud. Now, inside the storm cloud, there's wind going everywhere, and there's rain. So there's water droplets being blown around. Well, this radar signal bounces off of water droplets in the cloud. Okay, and so they receive they receive the signal back from different parts of the cloud. And if it comes back and the signal is 1,020 hertz, higher than what they sent out, then they know that the signal, that particular raindrop and the wind that was carrying that raindrop was coming towards the observer. Okay. In other parts, they might get a signal back and it might say 970 hertz. Okay, a lower frequency. That would come from a raindrop and wind that was going away from the observer. And you can program a computer to say, okay, for our wind profile, color all the stuff that's lower in red, color all the stuff that's higher in blue. And so if you had something like this, and if you saw something like this on your computer screen, what's going on here? If you saw this is your storm cloud. This is what's happening inside. What's going on? Well, here it's going away from you. Here it's going towards you. What does that mean? It means rotation. So they can see a tornado inside of a cloud before it ever starts snaking its way to the ground. All right? So, and since the advent of Doppler radar, and it's been around for like 40 years now, they have studied tornadoes and how they form from the very beginning, the birth of a tornado. And now, if you end up living in that part of the country, they won't bother waiting till the tornado's on the ground before the sirens go off. If they see something that might end up being a tornado, the sirens will go off, saying, everybody get inside, get to low ground, get to safety. We might have a tornado going on. Okay. So with the advent of Doppler radar, the detection and the knowledge of storms has increased exponentially. Okay. So if you end up being a weather person, you will definitely study stuff like this. Respond. Now, why does it work? Because of the Doppler effect. The whole thing, but at a whole different level. Okay. Okay. That's how Doppler radar works. Now, there's one other application of this. And I got to go back about 100 years ago now. Oh, by the way, I was out at lunchtime. Ms. Ewell pointed this out. It's the 21st day of the 21st year of the 21st century, which is kind of cool, actually. And so I got, that's kind of cool. So anyway, let's go back 100 years. There's an American astronomer by the name of Edwin Hubble. Maybe you've heard of him. Hubble Space Telescope, right? Still up there. And in my astronomy class, we'll look at pictures from the Hubble all the time. Never mind. So Hubble, he was an American astronomer. And at the time, 100 years ago, they thought the universe was our galaxy. They thought there was nothing outside of it. The universe was as big as our galaxy, and that's it. But then what Hubble did was he looked at something called island universes. They were little fuzzy patches of light in the sky. And he found out, well, there are other galaxies. I don't have time to tell that story. But he looked at other galaxies, and he looked at the light coming from those galaxies. Now, stars are made of hydrogen, and we know what the spectrum of hydrogen looks like. In fact, maybe towards the end of the year when you guys are here, I will show you, well, even if you're not, if it has to be for this, I will show you a hydrogen spectrum. And we know what frequency of light that is. It's very, very well known. The signature for hydrogen is a particular frequency. Actually, I know it by wavelength, 656 nanometers. But never mind. It's a particular frequency. They know what the frequency of hydrogen should be. Let's pretend that the frequency of hydrogen is 1,000 hertz. It is, and it's a lot higher, but let's just say this. Now, Hubble was looking at stars. If the star were stationary relative to us, then the frequency of that star's hydrogen would be 1,000 hertz. But if that star is moving relative to us, then it's going to be different because of the Doppler effect. Same thing. Okay. And what Hubble did was he looked at other galaxies. For example, well, that's a bad example. I was going to say Andromeda, but that's a bad example. He looked at it at a galaxy, and he expected to see 1,000 hertz light, but he didn't. He didn't get that. Instead, he got 980 hertz. Okay, so that galaxy is moving away from us. And then he looked at another galaxy, same thing. Then he looked at another galaxy, same thing. Then he looked at Andromeda. Oh, that was 1,010 hertz. Andromeda is actually moving towards us. In fact, we're on a collision course. In about 4.5 billion years, we're going to collide with Andromeda. Never mind, I'll say that for astronomy class. But there were a very few galaxies that are moving towards us. But the vast majority, when I say that, I mean well over 90%, well over 90% of the galaxies were moving away from us. Now, how did he know that? Because of the Doppler effect, the Doppler shift. And in astronomy, this is known as the redshift, okay, as the redshift, because the light is shifted down towards the red end of the spectrum. I'll talk about more about this when we talk about color. I want to come back to this. But they call this the redshift. Maybe you've heard of it. The Doppler redshift. Hubble found that no matter where he looked, you know, up, down, left, right, everything in between, he found the vast majority of the galaxies were redshifted and therefore moving away from us. And he found that the farther they were away, the faster they were moving. Okay, now, what does that mean? What does that mean? It means that in 1 hour, the galaxies will be farther apart from each other and farther away from us. Tomorrow, they will be farther apart from each other and farther apart from us. Okay? Okay, now run the clock backwards. Yesterday, they were closer. Last year, they were closer. 100 years ago, they were closer to us and closer to each other. Keep running the clock back. What does that mean? That means they were all at the same place. And as time moved forward, they were moving together. What caused them to do that? Well, a journalist like back in the 30s could say, what do you mean? There was some kind of big bang? You know, kind of derisively, but the name stuck. And that's where the Big Bang Theory came from. Who discovered it? Whose work culminated in the development of the Big Bang Theory? Well, Hubble, but he was using Doppler. Okay, this whole Doppler effect, that whole thing, taken with light, and we come up with all the evidence points to it. Now, nobody was around back then to write it down in their notebook, but all the evidence of what we know points to the universe being much smaller in the past. And if you study explosion theory, picture a firecracker going off, all the little bits of paper. The paper on the outside is moving faster than the paper on the inside. All the explosion theory stuff follows for a firecracker, and it follows for the stars. So it seems as if, okay, so the whole Big Bang Theory came about because of Doppler, right? So all this stuff. It's fun to talk about. Okay, Doppler effect. Questions, comments? It's fun to talk about. All right, now we're almost to our. Oh, yeah, hold on. Oh, almost fell off the table. Do you remember how I took the tuning fork and it was louder when it was on the board? Or, whoops. It's louder when I touch the table? The reason for that is because the vibrations of the fork are being transmitted down through the handle, okay? If I actually put this on my teeth, I can feel the vibrations on my teeth. Feels like a dentist drill, which you would do if you were here. Feels kind of funny, really. So the vibrations are carried right down the handle. And the vibrations down the handle cause the board to vibrate or the tabletop to vibrate. And since so much stuff is vibrating, since so much more stuff is vibrating, then it's louder, okay? I can also do this with an air column. I have a box here. I'm going to attach the tuning fork to the box like this. Check it out. Pretty loud, right? Because I'm forcing the box to vibrate at the same frequency as a tuning fork. And I'm forcing the air column inside the box to vibrate with the same frequency as a tuning fork. And so since I have so much more stuff vibrating, then it's louder, okay? Now we take advantage of that with one of these. Ms. Geffrey gave me one of these. Thank you very much. Okay. And she lent me a violin. I don't know how to play a violin. But this bridge right here, okay, the bridge, the strings by themselves wouldn't be very loud. But by transmitting it to the body of the violin and the air inside the violin, it can be the air in the violin can be caused to resonate. As we're really going with this, resonance, it resonates at the same frequency as the strings. So the strings transmit the vibrations to the body of the violin or the body of a guitar. And if you have air inside there also, I don't know how to play a guitar either. Wish I did. Here's where I need you guys in here. But the string vibrations are transmitted to the body of the guitar and the air inside, and it's caused to resonate. Okay? All right? Okay. But, let's see, what do I got? Oh, I got to end pretty soon. Shoot, I want to get a little farther, but oh well. Let's see. Hold on just a minute and see what kind of video. What do I have left in the video department? Oh, hold on just a minute. Do I have any pertinent? No. Got to save it. Okay. Sorry. Now, one other thing. This is super cool. Let's see. Okay, I'm going to leave you with this. I have this. I got to zoom out a little bit. Give me a minute. So I have two of these, right? And they are the same. They're both 440 hertz. They're both 440 hertz forks. I'm going to put them like this. I'm going to hit only one of them. Can you hear that? Yes, no? Put your volume all the way up. You could hear it if you were in this room. Can you hear that? This tuning fork made this one vibrate. Works better if I hit this one. Were you able to hear that? Okay. This tuning fork caused this one to vibrate. And the reason for that is these are tuned. These things are tuned to each other. They both have the same natural frequency of vibration. Okay, and because of that, we can transfer energy from one to the other. We can send it here and we can pick it up here if they have the same natural frequency of vibration. This vibrates. What do I got? This vibrates at 440 hertz, which vibrates the air at 440 hertz, which vibrates this air at 440 hertz. And this fork has a natural frequency of vibration of 440 hertz. And because of that, it can absorb, if something is vibrating at 440 hertz, it can cause this to vibrate also. The energy can be absorbed if they're tuned. This is called resonance. The fancy term for this is sympathetic vibrations, where the fork on the table would be forced vibrations. This is sympathetic vibrations. And there are lots of examples. And I ran out of time today. Some very dramatic, where you can cause things to resonate, sometimes for good, sometimes not so good. Okay, resonance, and I have a bunch of, but I'll show you those videos next time. Okay, I've reached a point where I want to stop, but one of the first demonstrations I'm going to do next time we meet is with a wine glass. Okay, and I'm going to make it sing if I have a good enough wine glass at home. I don't remember if I do or not. I always used to use a wine glass at my other school, but I left it there because it wasn't mine. But okay. So that's it for class today.